So I'd like to thank the organizers for inviting me to this very nice workshop, in particular to Jonathan. So there is as you notice, there is a change in the title of my presentation. The content will be, more or less the same. I mean, OK, so I'd like to present an algorithm for solving structured, non-convex, no-smooth problems, and to discuss the convergence properties, in particular to show that the segments of iterates we generate with this algorithm globally converges to a KKT point. I will define this notion later of the problem we consider. So looking at the non-convex world, non-convex, no-smooth world at this moment, what we have, we have algorithms for simple problems. Simple means, OK, proximal algorithm in a non-convex, non-smooth setting. We have gradient algorithm. We have proximal gradient, where convergence is proved by assuming critical relativity properties. And we have also the so-called PALM algorithm, which was mentioned in several talks in this workshop. But PALM one is again a proximal gradient algorithm. Okay, but we have two blocks, and in every block, in every component, the algorithm makes a proximal gradient step. Okay, but up to now, there are very few contributions related to the minimization of problems where compositions to linear operators appear in the non-convex setting. Okay, in a convex world, this class of algorithms are very well understood. So we have Shambol-Pock, so primal dual algorithms. We have other primal dual algorithms. We have ADMM, proximal ADMM. Okay, and all these algorithms rely on convex duality. And as I said 2 months ago, so for me the reason is, OK, so why do we don't have such methods in the non-convex world is, the reason is the lack of duality. So Terry said there is a duality in the non-convex setting, in the last workshop. There is one, but not a duality we need for developing primal dual methods, so-called primal dual methods in the non-convex setting. So I mean, if you want to extend the Shambol-Pock algorithm to the non-convex setting, you have to reinterpret the proximal step of the conjugate. But the conjugate is a notion which is related to the convex world. Okay, there is no conjugate for non-convex functions. So such an extension is from my point of view, is not natural. Okay, but still it is important to be able to address structured non-convex problems. And this is what I would like to do today. So present an algorithm, then look at some important things related to the convex analysis, and finally prove global convergence under critical relativity assumptions. OK, so this is the problem we are considering. So we minimize the sum of two non-smooth functions, proper lower semi-continuous. The first one is composed with linear operator. And we have here a coupling function which is Frechet differentiable. Okay, so everything is non-convex. Okay, and the aim is, as I said, to provide a full splitting algorithm to formulate. This is one of the most important aspects in the non-convex world, to formulate general conditions which guarantee that the sequence of iterates is bounded. Then to show that every cluster point is a KKT point for one, and to prove global convergence and to provide convergence rates in the setting of critical relativity property. Okay? So of course, we are actually very close in our formulation to this problem, which was investigated by Borsa-Bachtebor. Okay? So here we minimize fx plus gy plus h. Okay, and this is a so-called PALM algorithm. Okay, it was several times mentioned in this workshop. And what's happening here? So we make a gradient step and a proc step. Again, gradient step, proc step. This is still, if you want, a primal method. And of course, a naive approach when f is replaced by the composition, f composed with a, would be to put here a composition. But this is not what we want to achieve, to get, since we like to have a scheme where all functions involved, the linear operator, are evaluated separately, okay? And the linear operators by means of forward evaluations. So nonlinear equations should be solved or something like that. Okay? So the assumptions in this paper, okay, for analyzing the convergence of this algorithm are f, g, and h are bounded from below. Then the function, the coupling function, was assumed to be differentiable, gradient ellipsis continuous in both components. Okay, of course with ellipsis constants depending on the other component, and then we have here condition on the sequence of ellipsis constants. So boundiness, and a fifth assumption, the gradient was assumed to be ellipsis continuous in bounded sets. Okay, and in this paper it was proved that this sequence has all the cluster points of this sequence are stationary points, and then under Kudic-Alexeyevich assumptions, one obtains global convergence. And the question of boundiness, it's easy to handle in this context. Why? Since the Lyapunov function behind the analysis was the sum f plus g plus h. So if you have a primal method, it's very easy to construct a Lyapunov function, if you have, which you need, or the Lyapunov type function. If you have a primal dual situation, things become more complicated. Okay. So now, our problem looks more general. So we have here a composition with linear operator. And the algorithm which I like to propose is the following one. Okay? This is the method. There is probably at this moment very few intuition behind. So we generate a sequence in the product of 4 spaces. Okay? But what you probably can see is that we have here something related to ADMM because of this iteration. Okay, UN will be later the sequence of Lagrange multipliers. Okay, so we minimize in Y, in Z, and we have this step. Okay, and the question is, okay, how do you get such an algorithm? So what we have behind is actually a proximal ADMM, which is associated to our problem. And for the proximal terms, we considered some particular matrices, okay, and they gave rise to this scheme. This is a full splitting scheme. The non-smooth objects are evaluated by means of proc steps. Of course, set-valued operators, since f and g are only proper non-smooth continuous. We have forward evaluation gradient steps for h, and A is evaluated by means, again, of matrix times vector multiplications. So very easy to implement. Okay. And the question is, okay, can we guarantee convergence for this algorithm? This I'd like to address later. Now I'd like to discuss 3 special cases. This is the first special case where we assume that g is 0 and that the function h depends only on x. So we have the situation, composition of non-smooth with linear operator plus smooth. And this is what you get. This is, if you want, a primal dual algorithm. Okay, again, a full splitting scheme. Yeah? And so this algorithm is a particular case of our general method. And another particular case is the one which follows, which we get when looking at the same problem like in the paper of Bolsa-Bachtebul. Okay, but we get here a different method. But again, full splitting. And when looking at this problem, it means, f is 0, a is identity, h depends only on y. We get this problem, and this is the algorithm which results. This is the proximal gradient algorithm. Again, in the non-convex setting. And our analysis will cover the analysis of all these 3 methods. Okay? So, but what can we notice here is the following. So at this moment, we are not able to cover with this scheme the situation where we consider the minimization of the composition of a non-smooth function with linear operator plus a non-smooth function. So h is smooth here. Okay, and there is so we could get a scheme even in that case, and we can do a lot in improving convergence. The only thing is that we are not able, in the very general case, we are not able to provide assumptions or which guarantee that the sequence we get here is bounded. Okay, and this is why we have to work in this setting to assume. I mean, this is an important step, yeah? Since we have here a composition and we have a full splitting scheme, but still we like to have non-smooth plus non-smooth. Okay, And I will explain later why age smooth is important for boundiness. Okay? So, okay. So these are the assumptions. We are not very far from the assumptions in the Palm paper. Okay, we assume that the function h is differentiable in both components, and we have Lipschitz continuity of the gradient, and we have these upper bounds, okay, for the Lipschitz constants. We assume that a is surjective. Okay, so this is a strong assumption, and I'll come back later to this assumption. And at this moment, we don't assume that the function that h is differentiable. Okay, gradient of h is Lipschitz continuous on bounded sets. This comes later. Yeah. So we denote by psi star the infimum of this function, which is greater than minus infinity, and we like to look into the convergence analysis of this scheme, and the most important object here is the following function, okay, which is what? This is actually the augmented Lagrangian, okay, plus something. It's a regularization of augmented Lagrangian, and this function will be fundamental in our analysis. Okay, so we have here two constants, C0, C1. They are non-negative, and we have a matrix B, which is defined this way. And this matrix is not far from the matrix we use when obtaining Chambol-Poch or other primal dual algorithms for proximal ADMM. Proximal ADMM is what? ADMM plus two proximal terms defined by means of some matrices. And if one takes in the first arc mean such a matrix of this form, one obtains from proximal ADMM Chambol-Poch. I think Panos provide the details, actually. Yeah? And this is the same matrix. Okay. Good. So we have here augmented Lagrangian plus something. And what we need that the norm of B fulfills this inequality. And this is fulfilled in this setting. Okay, which is actually natural for primal dual algorithms to take step sizes in this way. These are some notations. Okay, and what we can prove is the following fundamental descent inequality. Okay, so this is a sequence psi n of objective values of the regularized augmented Lagrangian. And okay, if one gets such an inequality, then everything is more or less not easy, but straightforward. Okay, the only point is to guarantee that these constants are non-negative. And then one can argue in a classical way. Okay, so this is what you can prove with these constants. Okay, of course, as you notice here, we are using the minimal eigenvalues of A times A transpose, so they must be positive. Yeah? And this is why we assume that the matrix is surjective, and all the other variables which appear in the algorithm. Okay, and now by assuming that these three constants are positive, we obtain that the sequence psi n. This is, as I said, augmented Lagrangian plus something. It's bounded from below. It is convergent, and we get that these so-called discrete velocities, they all converge to 0. And this is an easy argument followed by telescoping. Good. Okay. Then the next question is, are we able to guarantee this condition? Yeah. Are there choices for the parameters of the algorithm which guarantee that these three constants are all positive? There are choices. Okay. These are some possible choices. Okay. So what we have here the condition number of this matrix involved. Okay. Then we can construct mu, beta, and tau, so such that this condition is fulfilled. And even more, we can solve these two quadratic equations, okay? And we can find solutions gamma 1, gamma 2, which are non-zero. And I'll explain later why is this important. Okay? So for the choice of beta here, we can find L1, we can find gamma 1, gamma 2 with these properties. Okay, so this looks very technical. So what I want to say is, of course, moving from convexity to non-convexity, okay, what we lose is the aesthetics. The convex world is beautiful, but problems are complicated. Okay, the next question is, okay, are you able to guarantee that the segment we generate is bounded under natural assumptions? if you stay in a primal world, in a primal space, then this is guaranteed by using some coercivity arguments. In a primal dual world, things are more complicated. Okay, but still, and this was our main aim actually, to provide natural assumptions for boundiness. Okay, and we have two situations when we can guarantee boundiness. Okay, and let me show you the techniques. Okay, and this will explain why do you need H to be smooth, and why we are not able at this moment to address minimization of the sum of two non-smooth functions. So, okay, these sequences are convergent to 0. They are bounded, as noticed before. Okay, then this is what you get. This is what you get from the previous inequality, from the decreasing property. So this means that psi1 provides an upper bound for this sequence. Okay, and now without this term, okay, we could argue by using. So this is actually the augmented Lagrangian reformulated, but this minus the Lagrange multipliers. Okay, this makes our life very difficult. Since because of this term, we cannot use coercivity, or we don't get from coercivity directly boundiness of these sequences. So we'll have to try to compensate this term in a certain way. And what we use here, we use the iterate un plus 1. Okay, this was the third line of our algorithm. Okay, and this gives rise to such inequality. Okay, and we have here a difference h minus something times norm greater than h to the power 2. This is a constant, this is fine, and everything looks good now. Yeah? Why? Since in the first case, I can keep on the left-hand side these two summands. I bring everything on the right-hand side and use the fact, okay, all these infimums are real numbers, and I use the fact that this difference is a real number. And this is the place where I use that I have such a gamma 1 such that this difference is equal to this term. Okay. Why it's important to have such a term? Okay, since for this difference, I know that this infimum, okay, is finite. So this is a consequence of the descent lemma. I have an upper bound for this infimum, okay, and this is a real number, and this is why I get that this infimum is finite, and okay, life is good. So again, in order to compensate this minus normal Lagrange multiplier, okay, I need something, okay, which makes use of the fact that H is differentiable. So for this inequality, for this difference, I need the descent lemma. Okay, and same argument in the second situation. Okay, now I get such an equality, and so everything on the right-hand side is finite. This is true for every n plus 1, for every n, and then from here, when H is coercive, I get everything what I need. Okay, same argument in the second case. But again, in order to get the diffimum with a real number, I need the descent lemma, and I need to compensate minus the norm of the gradient with the function itself. Okay, and at this moment, there is no other technique. Okay, so I'm not aware of any other technique. Okay, which allows me to guarantee boundiness of the segments we generate. This is because of the augmented Lagrangian, because of the linear term we have there. U times ax minus z, if you want. Okay, and we need boundiness. Of course, there is a huge literature which assumes segments is bounded, but okay, I sleep better when I know when the segment is bounded. Otherwise, it's very easy to assume. Of course, one can assume. If you would assume that segment is bounded, okay, then things would be much easier. Good. So we have boundiness, and now since we know when do we get boundiness, okay, then we can a little bit change the assumptions. We can assume the segment is bounded. So we have to now to use the fact that the gradient of H ellipsis continues on convex bounded set, okay, as in the Palm paper, okay. And this, by assuming this assumption 4, we don't need the other assumptions related to the Lipschitz continuity of the gradient of H in the first and second component. So we can remove that assumptions, okay. And the Lipschitz constants we had in assumption 1 are replaced by capital L square root of 2. And we get for C1, C2, C3, C4 easier formulas. But this is not the only choice. So there are also other choices for the constants. Good. OK, now, how to proceed? So what we know now, OK, we have a setting where we can guarantee we have a decreasing property. We have boundiness. Now we like to get a first result, namely to prove that, OK, we have subsegmences which converge. We prove that limit points are critical points. OK, and to this end, what I need a subgradient of the function psi of my regularized augmented Lagrangian. Okay, in terms of the limiting differential. This is the limiting differential. So let me recall that. Okay, this differential it was introduced as a limiting differential of the Frechet one. There is calculus, like okay, what you know is the local minimizer is a 0 of this object. Okay, if the function h is C1, then the differential is okay. It's containing only the gradient. We have a closeness criterion. We have a sum formula, not as good in the convex world. I said the convex world is fantastic, yeah. But we still have something. Okay, when h is convex, there's a differential coincides with the convex one. Okay, but by using this poor calculus, okay, we are still able to find a subgradient of our function. This is our Lyapunov function, if you want. Okay, and even more. Okay, we get an upper bound of the subgradient in terms of velocities, or differences of consecutive iterates. These are positive constants. Okay, and now having these properties, we can we get this is now a standard that for every critical point, first of all, this segment converges. Okay, to psi at this critical point. Okay, but for me the most important statement is the following one: the set of cluster points is a subset of the set of critical points of psi, and this is a subset of this set. Okay, and this set is the set of KKT points of my problem. Okay, and it is very important. Okay, now the question is why the augmented Lagrangian? Since the critical point of augmented Lagrangian provide me such inequality, which actually guarantees that the solution is feasible. Okay, so of course everything would be very easy if you would not have in our function the linear term. The boundiness is clear, everything is directly. But without the linear term, and this you can find in some other papers. Okay, you are not solving the initial problem. You don't get this. You don't get this relation. Okay, and what we know is that the function psi takes on the set of cluster points, this value. Okay, now what is this set? So this set, is the set of KKT points. Okay, so one can see that an element fulfilling this system of inclusions, qualities, fulfills these two inclusions. Okay, and we are now very close to the KKT point. When A is injective, we can use the calculus for limiting the differential and get that 0 is in this subdifferential. Okay, and which means that x star, y star is the critical point of our problem. Okay, but I'm still happy. Okay, even without these assumptions, to know that the segments which I generate converges to an element which fulfills this system, and this is a KKT point. Okay, of course, we are even in the smooth case, we may be very far from local minima, but that's life. This is what we are doing in the smooth case too. Yeah? Okay, good. Now, so this is what we get without any further assumption. Okay, now let us make our life nicer and assume that the regularized augmented Lagrangian is a curricular service function. Okay, this means it fulfills the curricular service property. This is a definition. Okay, and this is the idea which was used in relation to the convergence of non-convex algorithms. Probably, okay, I mean, the first paper I'm aware of is the paper of Ediatush with Jerome Bolt and with Bernard Zweig. They are very nice contributions. And so this is a definition of of a KL function looks very technical. It defined at the critical point of the function age. Okay, it is satisfied at every non-critical point. This is very simple property of the limit differential. Can be easily seen. And everything was motivated by the Loyasevic property of analytic function. Okay, so if h is differentiable, what we have here is the distance from 0 to the subdifferential. Okay, but if h is C1, then okay, this set contains only one element, and we get exactly this term, and this is the same with this property, well, which says that if we make a translation of the graph of h, okay, with h of x, and if we compose the function we get with a so-called decimalization function, okay, what we get is a sharp function. Okay, around the critical point. So this has a very, very nice geometric interpretation. And everything was inspired by the property, so-called Loyasevic property, okay, which is fulfilled by a real analytic function. Okay? So you can notice that by taking phi in this way, one obtains this inequality. Okay? And then this was extended to non-smooth functions. Okay, so very technical. Okay, what is the motivation of using such a property? Every good function is in this class. Every function you find in applications is a KL function. Okay, almost every function. I mean, the only function which I know which is not a KL function is exponential of -1 over x squared. Yeah. Probably there are also others, of course, but I mean, good functions are KL functions. Good. Now, assuming that the function psi in our object is a KL function, then what you get is that this sequence has finite length. Okay, and this implies that the sequence is a Cauchy sequence. Okay, and in that case, it's convergence. So the sequence we generate converges to, and this is what you already know, to KKT point of our problem. Okay, and this is the consequence of what we proved before plus KL. And of course, there are techniques behind this result. Okay, of course, you need estimates, you need this technical definition of the KL function, but what we finally get is such a property. Okay, and then by assuming that psi is a good critical Loyasevic function, is a Loyasevic one, where we have a Loyasevic exponent theta, we can prove convergence of the sequence of regularized augmented Lagrangians. Okay, and the question is, is there any reason behind having such a statement? Probably not. But from here we can derive, rates of convergence for the sequences we generate in our algorithm. Okay, so we have convergence in finite time. We have linear convergence and sublinear convergence. Okay, so this depends on theta. Okay, of course, such statements are known. Okay, in other settings, for proximal gradient for gradient, but not in this, if you want, primal dual setting. I mean, this is not a dual setting. This is a setting. Since, as I said, there is no duality in the non-convex world, or not a good one we can use here. But there is a linear operator, and there is a dual space, and even in this context, we are able to prove such statements. Okay, this is a list of references. So very important contributions. Okay, related to the use of critical Loyasevic property in algorithms. Papers of Edia Touche, Jerome Bolt, then Bolt, Sabach, Teboul. And this talk relies on this paper with Robert Chenek and Ko Nguyen. So thank you very much.